Now the delayed outward current behaves differently. It continues to grow monotonically with increasing membrane potential. Now, these observations together again provide evidence that this transient inward current reverses near 50 millivolts while the delayed outward current increases steadily. Now, knowing something about the ions that are present in seawater and having some sense of what the ionic contributions might be to the cytoplasm within axons, knowing something about the Nernst equation, and then having the ability to manipulate some of these empirical parameters in the experiment allowed Hodgkin and Huxley to identify what are in fact the ions that are carrying these two kinds of currents. What they concluded is that the early current is carried by sodium. Now, the Nernst equilibrium for sodium happens to be very close to plus 52 millivolts in their experimental preparation. That is highly circumstantial evidence supporting this conclusion that the early current is carried by sodium. One way to test that hypothesis would be to change the solution that is bathing the neuron. And if you substitute the solution with one that removes all sodium, the prediction would be that the inward current ought to reverse to become an outward current. Because even though the normal physiological concentrations of sodium are much greater outside the neuron compared to inside, if you artificially remove all sodium from outside the cell, there will be a concentration gradient favoring the efflux or the outward flux of sodium. And that appears to be what is recorded in this experiment. And then returning back to normal physiological conditions, similar to what we find in seawater, the inward current is once again restored. This conclusion is further supported by experiments using a toxin found in nature, a toxin called tetrodotoxin, found in the pufferfish. And when that toxin is applied to this axon, what we find is that the transient inward current is blocked. All we're left with is a delayed outward current with the application of tetrodotoxin. So that result provides additional empirical evidence supporting the conclusion that the early current is carried by sodium. Now, additional experiments were done using a tetraethylammonium ion, which is now known to block potassium channels. And when that ion channel blocker is applied to this preparation, what we find is that the delayed outward current is removed. And all that we find is the transient inward current. So this is very good evidence supporting the conclusion that the late current is indeed carried by potassium ions. Okay, well, I think we're ready to move on in our consideration of these data, and I want to introduce an additional concept that I think helps us come a little bit closer to the underlying biological mechanisms that explain the ionic basis of the action potential. And this concept that I want us to think about is conductance. Now, we're familiar with Ohm's law from our study of physics, right? And so Ohm's law is V equals IR, or voltage equals current times resistance. Well, this concept of conductance, while it has more of a formal expression, for our purposes, we can represent conductance by the lowercase letter g and simply state that it's comparable to the inverse of resistance. So it's possible then to rewrite Ohm's law in terms of current. And what we can state then is that measured current is proportional to the conductance for that permeant ion times the voltage. Now, this voltage term is interesting. This voltage term provides the driving force for the current that we can record that is passing through a neuronal membrane. But in order for that current to actually flow, not only must there be a driving force, but there also has to be some means by which that ion can pass through the membrane, which is to say there needs to be conductance. So I want you to appreciate, using this version of Ohm's law, that current flow really requires two kinds of functions. There needs to be conductance greater than zero, and there needs to be some voltage that creates a driving force term. And so rather than saying that the voltage needs to be greater than zero, what we need to express is that the voltage must be greater or different from the Nernst equilibrium potential for the permeant ion. Okay, so this allows us now to return to our experimental situation where we changed membrane potential and recorded current, but now we get to introduce this version of Ohm's law that helps us understand the movement of ions in terms of the conductance of the membrane for the permeant ion. So again, what we have here is current, which can be measured experimentally. We know something about the membrane potential of the neuron, and given the concentration gradient of the permeant ion, we know its Nernst equilibrium potential. So the driving force term then becomes the difference between the membrane potential at any point in time and the Nernst equilibrium potential for the permeant ion. So what would happen then if the membrane potential is exactly the Nernst equilibrium potential for the permeant ion? Under that situation, the driving force is equal to zero, and no net current is going to flow. This is one way to establish electrochemical equilibrium for a permeant ion. That is, it's possible with the patch clamp method to set the membrane potential exactly to the Nernst equilibrium potential for the ion in question. Well, this formulation should make it obvious that there is another way in which to have no net current flow for an ion, and that is when conductance is equal to zero. That is, when there's no means by which an ion can cross a membrane. There may be a driving force, but if there's no conductance, then the measured flow of that current is going to be zero. Okay, well, these are some theoretical ways of considering the experimental results obtained by Hodgkin and Huxley, and what's shown now in the lower part of figure 3.3 are the same data, except now the measured ionic current is expressed in terms of the conductance that is associated with the transient current and the delayed outward current. Now having confidence that that transient current is carried by sodium and the delayed current is carried by potassium. So what we can now do is express these current fluxes in terms of conductances for sodium and potassium. So let's look at these one at a time. When we look at the conductance change for sodium with depolarization, what we see is a very sharp and steep rise in sodium conductance that happens with increasing depolarization. So it should be obvious then that the sodium conductance is voltage dependent. But look what's going on here. Even with a sustained depolarization, this conductance that quickly rises well above zero falls back towards zero, even though we continue to clamp the axon membrane to some value, as indicated here in the figure. So this tells us that this conductance is not only voltage dependent, but it's also time dependent. Actually, the same conclusions can be made with respect to the potassium conductance, but in a different way. What we see is with increasing depolarization, there is a growth to this potassium conductance. So like the sodium conductance, there's evidence for voltage dependency. But notice the growth is gradual, and the onset of this conductance is relatively slow compared to the onset of the sodium conductance. So there's an element of time dependency that we see for the potassium conductance. Now, that conductance does not fall back down sharply the way we saw for the sodium conductance. Rather, the time dependency is in the relatively gradual onset of this rise in potassium conductance that we see. So, nevertheless, both conductances are time dependent, but the time dependency seems to suggest that there may be different molecular mechanisms that mediate those time dependencies. Okay, let's return now to the sodium conductance and make an additional point about this rapid fall in sodium conductance that we see after the rapid rise. So we actually have a term for this. We call this inactivation. Now, as we'll see in the next tutorial, inactivation is not exactly the same mechanism as simply closing an ion channel. So we're going to want to understand that point in the next tutorial. But for now, I'll just highlight the fact that the sodium conductance inactivates. And what we mean by that is this rapid fall in conductance that follows the rapid rise. Now notice the potassium conductance does not inactivate. So there's no inactivation of the potassium conductance. Now there are certain types of potassium conductances that can be found in certain neurons that do in fact inactivate, much like the sodium conductance, but not this conductance, not in this axonal membrane from which these experiments are derived.